So here we are in week 12. It's Monday, we've got our live class meeting. We are starting chapter 5, probability. We're going to look at introduction and section 5.1, or part of section 5.1. We have our live class resources here, as we usually do. As you can see, it's starting to be populated. Right now, we do have an AP Daily video that applies to what we'll be talking about today in class. I also do have the section of the textbooks that our lesson applies to today, if that is something you would like to refer back to. Okay. And then we have a discussion board for today. It is what are the odds? This has to do with probability, a basic understanding of what different probabilities mean within context. This will make more sense at the end of the lesson. And I will review that at the end of the lesson so that we all know what is expected. There will be a self-assessment for chapter 2, which is the chapter we finished last week. This suggested due date on this is 2 weeks from now, right, November 23rd. All right, I'm giving you 2 weeks on that. And again, based on what we just discussed, the past 2 weeks, it will be entered in as a missing assignment, and it will affect your grade if it's not submitted. Okay. So we'll have another self-assessment here. I'm finishing that up. I should have it done and ready today. And then we'll move into completing section 5.1 on Thursday. We're going to do with like simulations, probability, and all that fun stuff. And that will be the week. Any questions about this week? Alrighty, so here we are. It is Monday, November 9th, 2020. We're going to look at what we've covered so far, where we've been, and what we're going to be doing next, where we're going. I'm going to go through this, what we've seen so far, relatively quickly, because these are all things that we've done and we have notes on already. First, we covered chapter 4, that was on designing studies. Section 4.1 was sampling and surveys. We discussed how to sample. It covered things such as convenience sample, voluntary response sample, bias, random sampling, simple random sample, stratified random sample, cluster sample, undercoverage, non-response, and response bias when we discussed how to sample. We then went into section 4.2 about experiments. We considered an observational study versus an experiment, the difference between those two. In an experiment, we have treatments, experimental units, and subjects. When we want to experiment, well, we must consider these 4 things: random assignment, comparison, control, and replication. These are the 4 characteristics of a well-designed experiment. We want to use completely randomized design when we design an experiment. That means we randomly select the population for our experiment, and then we randomly assign them to the treatments. Right? It's like double randomized. Within experiments, we considered things such as the placebo effect, and then how to do a double-blind study or a single-blind study, and what would make something statistically significant. We also looked at block and randomized block design and matched pairs design. Lastly, we discussed the scope of inference. When can I make an inference based on how the study was designed? Right, can I make an inference about the population or just about the sample? Right, those types of things. And then for chapter 1, which we did next, about exploring data. We first wanted to make sense of data. We discussed what's an individual and what is a variable. Individuals are the people or things or objects that we are studying, and the variables are the things we are measuring about those individuals. Right? We can have categorical variables and quantitative variables, And when we look at those numbers, those results, those create a distribution. Right? Categorical variables are like categories, like being male or female, right? Those are categories. I can't find an average for those things. Right? A quantitative variable is something that is numerical, and I could calculate an average if I wanted to. With categorical data, we can make a bar graph, a pie chart. We have two-way tables, marginal distributions, conditional distributions, and between those things, we are hoping to make an association. Quantitative data, we can represent with dot plots, histograms, stem plots, back-to-back stem plots, split stem plots. And we always want to talk about shape, center, spread, and outliers, which we can remember by using our SOCS or CUS. Quantitative data can be described as symmetric or skewed, or unimodal, bimodal, or multimodal. When we describe quantitative data, we must talk about the center, which can be the mean or the median. We would choose one of those depending on the distribution. Right? Typically, something that is symmetric is more well represented with a mean. Something that is skewed is more well represented with the median, which then leads us to the spread. No matter what, it looks like it's always going to have a range, the minimum to the maximum. The IQR is more applicable for a measure of spread for a skewed sample. A standard deviation is better for a symmetric sample or a symmetric distribution. We want to be able to identify outliers. We explored using the 1.5 times IQR rule. We can also use more than 2 standard deviations away from the mean if we are using the mean as our measure of center. We can create box plots from a 5-number summary, and we want to use these things to compare distributions. Then we got into chapter 2, modeling distributions. We need to be able to describe the location of a distribution. We can do that with percentiles, cumulative relative frequency, standardized score, the z-score. And we also considered transforming data, adding or subtracting a number, or multiplying and dividing by a number to adjust our data. Right? Standardizing the score is one version of transforming data. That led us to density curves and the normal distribution. A density curve has an area of 1 under the curve. The mean and the median of a density curve depends on the shape of that curve and how they are related to each other. A normal distribution, which we can annotate with n parentheses mu comma sigma. Mu is the mean, sigma is the standard deviation. The mean and standard deviation completely describe a normal curve. We considered the 68, 95, 99, 7 rule. Standard normal distribution, table A, and making comparisons with z-scores, which brought us to doing calculations with the normal distribution, where we would be able to find the proportion of a curve based on a given value, or find a value given a percentile or proportion of a curve. All right, this was one of the last things that we did. And the last thing we covered was assessing normality. Right? If something is approximately symmetric and bell-shaped, close to the 68, 95, 99, 7 rule, then we can say it could be approximately normal. We have strong evidence for it to be approximately normal. Another tool in deciding if something is approximately normal is the probability plot, which we can get on our calculator. All right, so this is what we've done so far. It is a good chunk of stuff. I wanted to make sure to take the opportunity to kind of look at it, look at the key things and vocabulary and concepts that have been covered, because we don't want to forget about these things. They're going to come back up. We're going to need to be putting these things together. Okay, so now, what is next? Probability, as was alluded to. Right? So this is going to be our next chapter, is probability. I enjoy it. I think probability is kind of fun. Right? So chance is everywhere. Right? Rolling a dice. Right? There's equal chance of getting any of the 6 sides of the dice based on probabilities. Flipping a coin. Right? You have 50% chance of getting heads or tails. Again, chance. When you play rock, paper, scissors, right? Theoretically, you have a 1 in 3 chance of winning. right? Playing the lottery, most of us don't have a great chance of winning that, right? Playing slots always kind of leans towards the favor of the house, right? They usually win, but there is a chance, right? There are these probabilities around us in everyday life, the chance of something occurring, right? Other kind of like examples could be genetic inheritance, right? There's a certain chance that some of your characteristics will be passed on to your offspring if you choose to have kids, right? But the other parts, like from your partner, also play a role in that, and it becomes a whole mix of things, and there's a chance of certain things happening, right? We have simple random samples, right? When we randomly select people to participate in a study and then we randomly assign them, there's a chance, there's probabilities and chances happening within that that help kind of decide the outcome, so to say. Right, so chance is everywhere. Okay, so first, we're going to play a game. All right, we're going to collect some data. So I'm going to put a couple of things in the chat, and then we'll go over the directions here. As a special promotion for its 20-ounce bottles of soda, a soft drink company printed a message on the inside of each bottle cap. Some of the caps said, "Please try again," while others said, "You're a winner." The company advertised the promotion with the slogan, "1 in 6 wins the prize." The prize is a free 20-ounce bottle of soda, which comes out of the store owner's profits. 7 friends each buy one 20-ounce bottle at a local convenience store. The store clerk is surprised when 3 of them win a prize. The store owner is concerned about losing money from giving away too many free sodas. She wonders if this group of friends is just lucky or if the company's 1 in 6 claim is inaccurate. In this activity, you and your classmates will perform a simulation to help answer this question. For now, let's assume that the company is telling the truth and that every 20-ounce bottle of soda it fills has a 1 in 6 chance of getting a cap that says, "You're a winner." We can model the status of an individual bottle with 6-sided dice. Let 1 through 5 represent "Please try again," and 6 represent "You're a winner." Right, so you guys are going to roll your digital dice 7 times to imitate the process of the 7 friends buying their sodas. You're going to, in the Microsoft form, you're just going to input the number of wins in your 7 rolls. So if you only roll 1 6 when you do 7 rolls of the dice, you're going to put in a 1. Right? So then we're going to collect this data, and I'm going to create a box plot using Statplit so that we can look at the data and then talk about it. All right. I will also encourage you to submit the form more than once. So I'm going to give us 5 minutes to do this, to roll our dice and input our data. Please do the simulation as many times as you would like and submit the form as many times as you like. You can submit the form more than once. The more data, the better. Okay. I will also have some data to input. So that's what is going to be. Are there any questions? All right. If you're in the middle of inputting data, please input it. Otherwise, I'm going to use our results. Here's the results. All right. So we collected all of our data. What do you notice? What's the first thing that jumps out at you? What do you guys see? What do you guys notice? What's interesting? Thought there'd be more 1s, right? All right. What else? Okay, Arlen thought there'd be more 1s. Seems reasonable. What else do you notice? If we're thinking of this as like a distribution we'd want to describe, what other things could we say? The 6 is just out there, right? Someone managed to win 6 times out of 7. Someone won 5, someone won 4, right? It's skewed. Okay, which direction is it skewed? Come on, guys. more people. Yeah, got Arlen answering right now. Here we go. To the right. Yes, it is skewed to the right. The tail would be to the right. Blah, blah, blah. All right, which means it is skewed to the right. Right. If we draw over it, we go. All right. So we have a skew to the right, which kind of makes sense, right, based on our median of 1, and the mean is pulled to the right, 1.6, 1.5, right? Let's see. What else? What else can we say? Does it make sense for the company to claim that 1 in 6 wins? What do you guys think? Yusef says no. Why? Why does it not make sense? I like that you say it doesn't make sense, but I want to know why you think that.
It would be 1 out of 37 because it was the data shows 37.
Correct.
37 points.
We have 37 data points. That's the value of n. That's the number of trials we had, so to say. And we had 1 occurred 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. So 11 out of 37. What is that? So that is 0.29 or almost 0.3. Is that the same as 1 out of 6?
No, it's like 1 out of 4 almost. Or
Yeah, it's between 1 out of 4 and 1 out of 3, right? 1 out of 3 would be like 33. 1 out of 4 is 25, right? So we're somewhere in between, right? So when we're thinking of probability, we're also thinking of proportion, right? What's the proportion of my data that falls within a certain value? Right? In this case, right, when we do the math, we see that proportion-wise, we have 0.29 rounded to 0.3 was 1 win. So the chances of 1 win happening is 0.3. Now we have other probabilities happening, right? And there's more that goes into making the statement of 1 in 6 wins, which we'll get into. But yeah, I mean, if we just look at the data, we have up to basically 0, 1, 2, and 3 wins, right? Within this sample data is relatively close, right? They're only off by a couple in each one. So is this enough to say that there's a probability existing? Is 37 trials enough? Or would it make sense to do many, many more trials to try and get a better idea of what we would expect to happen? All right, well, let's move on to the next part here. More trials is always better, yeah. Yeah, so you said, yeah, more trials is always going to be better, right? And it turns out, and we'll see in the next couple slides here, in order to make a statement about probability or to establish a probability, we need many trials, right, to establish like an actual chance or pattern of something. Right? This could give us an idea, right? Could maybe allow us to make an inference or an association, but it's not enough to like say, okay, well, the probability of this happening is a number. Right? So what is probability? An important fact emerges when we watch coin tosses or the result of random sampling and random assignment closely. Chance behavior is unpredictable in the short run, such as what we just did with the rolling of the dice. We weren't sure what was going to happen every time we rolled the dice 7 times, but it has a regular and predictable pattern in the long run. So the more data we collect, the more predictable things become. This is the basis for the idea of probability. Probability describes what happens in very many trials, and we must actually observe many outcomes to pin down a probability. So this is essentially like what Youssef said, more is better. It helps us pin down what we expect to happen. The law of large numbers, which is a thing, states that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. This value is called the probability. All right. So, yeah. Here we go. You raise your hand if you need a moment to write any of this down. Okay. So let's look at something real quick because we have time. All right, so here's this little applet, right? That is, I have it linked in the live class resources for today as well. And what this does is this simulates flipping a fair coin, right? Fair, right, meaning 50-50 chance. We can change the fairness of the coin if we wanted in this applet. And so if we simulate 15 tosses of the coin and keep track of the number of heads and number of tails, I'm going to have this line here that shows the true probability. We run the simulation here. The blue line is tracking the number of heads, right? We end with 0.6 heads and 0.4 for the probability of hitting tails. But we can see how this blue line starts moving up towards the 0.5. If I increase this to 50 simulations, it's going to keep going. Notice how the line is bouncing around, really, and it keeps kind of coming back down or getting closer to the 0.5. This is what it means is it starts, like the values start to come to a point here. Start to converge on a value. We do more simulations. We expect this to get closer and closer to 0.5. Now, it may never be exactly at 0.5. This allows me to go up to 200 simulations. And so I've run 365 simulations. I got 186 heads and 179 tails. We're getting closer and closer to that 0.5. If I just keep going and keep doing more and more and more and more, it's going to get closer and closer and closer. This is what we mean by we need many observations and many trials. And you can play around with this if you like. It's in the stuff. So here we go. So that's what it means about approaching a single value. This is the actual definition of probability from the textbook. Right? The probability of any outcome of a chance process is a number between 0 and 1. Just like the area under a density curve is 1, right? We don't use 100%, we just say 1 to represent the whole thing. We do the same thing with probability. That describes the proportion of times the outcome would occur in a very long series of repetitions. Okay, outcomes that never occur have a probability of 0, like 0%. An outcome that happens on every repetition has probability 1, 100%. An outcome that happens half the time in a very long series of trials has probability 0.5, such as flipping the coin. Probability is measured in the decimal representation of percentages from 0% to 1, or 100%. Right? It is not very common to write the probability as a percentage. You can say, hey, this thing has a something percent chance of happening, but it has a probability of, or probability 0.5, or probability 0, probability 1, probability 0.75. It uses that decimal instead of the percentage. Okay. All right. Can you raise your hand if you need a moment to write anything down from this slide? Nope. Okay. So then, that's the end of the slides. So let us now look at discussion board. All right. So our discussion board for today says, according to the Book of Odds website, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Right, for this, you want to explain what probability 0.61 means in the setting. Right, what percentage of adults are expected to eat breakfast, essentially. What doesn't this probability say? Why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them usually eat breakfast? Why is that not the statement they're making? Why are they saying it the way that they did? Okay, think of, is sampling 100 U.S. adults enough to make that statement? And then there's a matching problem. Probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follows with each statement. Right. There is 4 statements and 6 numbers, so they're not all going to be used. All right. Last thing that I wanted to review that isn't necessarily about a specific problem is there has been some frustration slash confusion about getting pictures inserted into your responses, such as if you did your work by hand and you would take a picture of it and you want to upload it. Depending on the text editor that you have enabled within Canvas, the way to do that is different. All right. I'm going to use this to demonstrate. Some of you have this text editor enabled. It is the Enhanced Rich Content Editor, which makes embedding and inserting pictures much easier. So this is actually what I would recommend to use as the text editor. The other one, essentially the best you can do is attach the file of the picture, which I could then click on and download and view. But if you want to just embed the picture, in this editor, it's a lot easier to do. To change that, you will go to your settings within the course. under your feature options, you should have the option for the rich content editor enhancements, this RCE enhancements. If you turn that on, then the editor will look like this, where you have this, like, it kind of looks more like a word editor, right? You have options across the top here, so you can insert an image and you can upload the image. You can literally drag and drop your .png file, which Canvas prefers as far as like embedding an image. It likes .png files. It doesn't always cooperate with JPEGs or the high efficiency image, whatever ones from Apple. So if you can save them as PNG files, that Canvas seems to cooperate with those the best. Yeah, you can drag and drop or find it on your computer, whichever you'd like. So that editor seems to cooperate with uploading pictures better. If you are using the other editor, which means this is turned off, then the editor looks like this. Most likely the best you can do, right? If you click on here, it's going to ask you for an embed code. That's not going to cooperate. If you go into Office 365 and you've saved your image into your files in Office, right, you can attach the file, attach the image as like a clickable file. Right, so if I do it that way, I can just click in and say, okay, I want my PNG file here, and I can attach the file. All right, so it won't show the image, but I'll be able, as like the teacher, I can click on it, download the image, and look at it. All right. So depending on the editor you have enabled, the way to attach an image is slightly different. And I wanted to review that so that you guys can do that. Because oftentimes it might be easier to do your work on like a piece of paper and then just take a picture of that and upload it, rather than trying to get the text editor to do all the things you want it to do. Right? And also it can make it so like if you've done something within Stapplet or Desmos or something else that has generated Excel, that's generated your graph, you can take a snip of that graph, upload it in, make it a little easier. All right?